Um, my name is Jongho Park, and welcome to the Signals and Systems course. Okay, we are currently at Chapter 8, which is about this discrete time Fourier series. So the derivation for the discrete time Fourier series is similar to the things that we did with continuous time. And also, it's the same thing that we start with the periodic signal, which leads to the Fourier series, and then we will extend it to the non-periodic signal, which we will do it today, and which will lead to the Fourier transform of the discrete time. Basically, it's the same idea, but we have some difference between the continuous time and the discrete time, such as we can limit the summation, the number of summation for one period, because the same thing repeats after like the same values repeats for over the periods. So we don't have to deal with the whole thing. We just set the range of this summation for just one period. And unlike continuous time, discrete time has a closed form solution for obtaining this AK. We have n equations and n unknowns, which we can have this closed form solution, and that leads to the analysis equation for the discrete time. And also the synthesis equation is about the linear combination of this complex exponential. So we had these differences. Please notify this. And we can see from the first example that the coefficient AK is periodic. We can see it from the real part and the imaginary part, also from the magnitude and the phase of the polar form. And with this kind of square wave, we actually obtained this AK for the Fourier series. So with this formula, we have arrived to this form. However, if I may, I want to express them in the sinusoidal wave. Therefore, if you've done that, I can have this formula, this solution, where we have to put large omega as 2 pi k over n. So only the harmonically related frequency can be used for this large omega. So if you compare to the continuous time for continuous time square wave, the square wave in continuous time looks like this. I have this kind of form from minus t1 plus t1, and since you have to have this periodic signal, if my period is t0, then you will have another square wave here, and if I have minus t0 here, I will have square wave like this. And if you try to obtain this AK for continuous time square wave, then you will get you will get 2 times sine of omega t1 over omega, where omega should be 2 pi k over t0. And I have told you that this AK is periodic only for the discrete time, and you can verify this property with this example. I mean, you can see that the AK is periodic because it's sine something over sine something. However, as you can see in this continuous time case, it is sine something over just something. So this omega decreases. Excuse me. If this omega increases, then the whole AK will decrease. So it's not periodic for the continuous time with the same square wave. So, and in discrete time, this AK is periodic, and if I import this AK in the textbook with the same Okay, I think something's wrong with my iPad. I'm not sure why this is not working. Okay, so finally I have it here. So if you plot this large N times AK, when then it goes like this with N equaling 10, 20, and 40. So you have seen this property when we were dealing with continuous time. And also, we can say that this envelope here is periodic, right? Because AK is periodic due to the things that we learned with this discrete time. So AK is definitely periodic, and you can see that the coefficients AK for this Fourier series is a sample of this envelope. And this envelope gets denser and denser as n increases, like this. So if n goes to infinity, then you will have infinite samples, which means it will become the envelope itself, okay? So if n goes to infinity, then the coefficient will be envelope itself. Okay. So please remember that with the continuous time, it's not periodic, but with continuous time, the Fourier series coefficients have the periodic property. And also, as n increases, this getting denser and denser, we observe this property also in the continuous time. Okay. Okay, so with the periodic non-periodic signal, now we will focus on the non-periodic signals. Before that, we will review the process that we did with the continuous time. And as xt is non-periodic, then what we did was to construct a periodic signal. We denoted that as x tilde, right? For which one period is xt. And we know that the periodic signal x tilde has Fourier series, right? And if you increase the period of this x tilde, then x tilde becomes xt, and Fourier series of x tilde becomes Fourier transform of xt. And now we will apply the same strategy to the discrete time. So, and the only thing you have to do with this derivation is to make xt xn. Okay, so I'm not gonna rewrite the whole thing because it is practically the same derivation that we have done in continuous time. Okay, so like the only thing you have to do is to switch this round parenthesis to the square bracket. So the Fourier representation of non-periodic signal, of course, for the discrete time. And okay, so this is the basic strategy, which is equivalent to the one with the continuous time. So you will, if I want to obtain the Fourier series of just this discrete time signal, then you have to replicate this to become x tilde like this, to make it periodic, okay? And as I increase this period n to infinity, like we did with this example, right? So I mean, we already obtained this envelope from this example, as we have observed that the interval between the AK becomes smaller and smaller, which means it gets denser. So it'll become the envelope itself. So we're like doing the same thing to represent xn. So we use the Fourier series to represent x tilde, and then we will increase n. So the period becomes infinity, and so this means we have every point of the envelope, as we have witnessed in the previous example. And so it just becomes the envelope itself. Okay. And I'm not gonna derive the two equations for Fourier representation, because it's basically the same derivation. So I'm just gonna write the thing. So x tilde, you can refer to the content that we did in continuous time, okay? So x tilde is like k summation of one period 1 over 2 pi times large X k omega 0 e to the j k omega 0 n large omega 0. So this is the synthesis equation using the envelope function, right? So this is the synthesis equation using the envelope function. And this x of k omega 0 is n times ak, and this I can say the summation for one period. So I start with minus n over 2, then I have to finish with n over 2 minus 1. E to the minus jk omega 0 n. So once again, I'm not going to derive the things to obtain these two equations. You can refer to the things that we did in continuous time. And please compare these two equations with the equations in continuous time for your own good, okay? And as you increase large n to infinity, then it becomes the Fourier transform. And I'm just going to write it. So the Fourier transform xn is 1 over 2 pi integration of just one period of x of large omega e to the j omega n d omega. And this is the synthesis equation for the Fourier transform of discrete time. And of course there will be an analysis equation which is obtaining large xn. And this is the summation from minus infinity to plus infinity with minus j omega n on the top of the exponential. So this will be analysis equation. So we can point out some things for this Fourier transform of discrete time. We know that xn is discrete because it's discrete times signal, right? However, this large x omega is continuous, and you know that this is an envelope that we try to depict here, right? So xn is discrete, however, this large x omega is continuous, and that is the envelope. So the one thing is that xn is discrete, however, large x omega is continuous. I can better point out that this is the envelope if you plot this x of omega. And we know that we are now covering the general case where xn is non-periodic. However, recall that ak is always periodic. Therefore, x omega is periodic with a period of 2 pi. Okay? So even though xn is non-periodic, this Fourier transform of xn is periodic with 2 pi. Okay, these two properties you should remember for the Fourier transform of discrete time. Okay, the first example for the Fourier transform now is rectangular pulse. And I'm not gonna go through the whole this whole derivation, but so this is obviously non-periodic signal, discrete time signal, and if you obtain the Fourier transform of it, then you will get sine of 5 omega over 2 divided by sine of omega over 2. So this is a periodic function, right? If you plot this thing, then you will get this one, and it's a periodic function with period 2 pi. So you can, if you cut from 0 to 2 pi, then you can see that this thing repeats infinitely, right? So I can verify that you have the period whose value is 2 pi. And we can see that this Fourier transform is a periodic function, even though xn is non-periodic. So you can see this property right from this example. Okay, the second example is the decaying exponential. No, I'll stick to this EX. And I think I have the plot for this also. This is not right. Yep, so decaying exponential is we have this kind of discrete time signal, and I can formulate this xn as a to the n multiplied by the unit step function. And you can see from this figure that a is the value between 0 and 1. Okay, so this time I'm gonna obtain this Fourier transform by myself, and I'm gonna just use this equation here. I'm gonna use the definition. So this xn is a to the n times un times e to the j minus j omega n, right? And you can see from this unit step function that this function vanishes as we modify the range of the summation, because you have zeros for the negative n. So this becomes summation from 0 to infinity, and this un vanishes with that by taking that part off. So n becomes, the summation now is from 0 to infinity with an n. And I can say we can combine them too with this parenthesis. We will again use the formula. We will use this formula one more time for this example, and if you use that example, then it becomes 1 minus a e to the j omega r plus 1. Oh, excuse me. I have to take the limit, right? Because I have to go to the infinity instead of the r. I have to set this infinity, and we have 1 minus a to the a times e to the j pi. Omega. And we know that a is between 1 and 0. So if r goes to infinity, then because of this value, this will go to 0 because of this. Okay, so now we can simplify the function for this example. And since it involves j here, we now definitely have the real part and the imaginary part. So we can make that complex function into the polar form, and if you obtain the magnitude and the phase, then you will get this kind of two graphs to represent the magnitude and the phase of this Fourier transform. So the upper one is the magnitude and the other one is the phase. Okay. So we can see from this magnitude and phase function that this, even though this xn is non-periodic, the Fourier transform is periodic because we have a periodic graph for the magnitude and a periodic graph for the phase. So their combination should produce the periodic Fourier transform function. And we can also see that the period is 2 pi, right? From minus pi to pi, and 0 to 2 pi. Okay. And just one more thing about this equation, this example. What if A is A is from minus 1 to 0. What if it's a negative value? Then I'm not going to do the whole thing again, but if this happens, then this magnitude function, if you obtain the magnitude function of Fourier transform for this range of A, then the magnitude function will be shifted to the by the amount of pi. So I think it will become like, this. Okay? If I have this range of A, so you can switch this 1 over minus A and 1 over 1 over 1 minus A and 1 over 1 plus A to represent this Fourier transform for this range of A. And we will cover this in detail when we study the filtering, which is, I think, in a couple of chapters that we will study more thing about the filtering, and I think we will cover this function one more time. So if A is from -1 to 1, then you can see that the magnitude function will look like this. Okay? Okay, so I would like to extend the Fourier transform to observe the Fourier series as we did in the continuous time. I mean, the periodic signal periodic signal resulted in the Fourier series, whereas the non-periodic signal resulted in the Fourier transform. However, we can use the Fourier transform to express the periodic signals. So, as we have written the following statement in the Fourier in the continuous time, it's the same concept that Fourier series coefficient, which is represented by the AK of the discrete signal periodic, which is periodic, is same as 1 over n multiplied by Fourier transform of xn. So this is this is completely the same concept as in continuous time. So if I say xn is just one period of x tilde, and then x tilde is a periodic signal, so we can obtain the coefficient of the Fourier series, and that coefficient can be represented by 1 over n times the Fourier transform of xn. Okay, so we can say that AK is 1 over n times large xn omega, where omega should be, I can say that a multiple of sigma 0 or 2 pi k over n. It's the same thing, right? So it's like harmonically related frequency that can be inserted into this omega. And also, so the same picture that we have used, nope, not this one. Okay, so we start again. So this was for the square wave, right? This was for the square wave. And I'm not gonna plot this wave again. However, so what I want to say is this square wave was a periodic signal, and that periodic signal has the coefficient for the Fourier series, and those are these values here, and that value belongs to this x omega, which is this envelope here, right? And with that envelope, you can just insert this variable as the multiple of omega 0, which are marked like this. Okay? And if you divide that value by large N, then you can obtain this AK. So that's the point that I wanted you to have. And also, if x tilde is periodic, then we can represent it by the Fourier transform. And the Fourier transform of that x tilde n can be defined as a linear combination of impulses, which is exactly the same concept that we have witnessed in the continuous time. So k starting from minus infinity to plus infinity with 2 pi ak, you remember, with the shifted impulse by this multiple of omega 0. So it is perfectly same thing. And with a square wave, I can have this example. I'm not sure why I haven't I think I forgot to involve this figure. Okay, so I'm just gonna draw it by myself. So if I have this 오늘은 사진 찾는데 너무 시간을 많이 쓰네요. 죄송합니다. So if I have this periodic signal, and its Fourier series coefficients can be represented like this bar graph, right? Because it should be discrete. And that I can express it like this. And please notify the value for x-axis for this one. So it'll be like So 0 you will have like this much, and 1 you will have this much, 2, 3, and then 4, and then 5, and 6, 7. So 7 and 3, they should have the same value. It goes like this. So I didn't draw the envelope that it always had, like this. If you see this plot, we always had this envelope, but I will not draw the envelope for now. So this is the value for Fourier series coefficients. And if you obtain the Fourier transform, then you will also get the sequence of impulses. Okay, so it goes like this. And please notify the difference of x-axis, because now we are in the frequency domain due to this Fourier transform. So we can use this Fourier transform by the impulses. No, I'm not going to say by, just by impulses. And those would be like zero, omega 0, so the pattern looks exactly the same. However, you have k as a axis for Fourier series, and you have the frequency for the axis of the Fourier transform. And you can use the shifted impulses, delayed impulses, to represent the Fourier transform of the periodic signal, like this. So with this formula, you can have this equation here. Okay, so we have gone through this discrete time Fourier series and Fourier transform, and as you have experienced, a lot of things have the same concept as in continuous time. However, there are some differences, right? So to express that difference, I want to make a small table here. So we will have a continuous time and we will have a discrete time. And there, for continuous time Fourier transform, there was a duality between time domain and frequency domain. However, there is no duality in discrete time, because in time domain, the signal was represented by the discrete time value. However, in frequency domain, the Fourier transform is the continuous time function, remember? So we can have this duality. So time domain, you have discrete representation. However, even though you have discrete signal, if you compute the Fourier transform and hand over to the frequency domain, then you will have that continuous time. representation. And in continuous time, you have to cover the entire frequency. However, for the discrete time, you have to cover only one period of frequency, which is 2 pi. And outside this period, the function repeats itself, which becomes a periodic signal, and therefore in frequency domain you have a period. So in frequency domain, the period exists. So that's why what I wanted to point out, the difference between the continuous time and the discrete time Fourier transform, and also Fourier series. Okay, and now I think we can move to the next chapter. Okay, so chapter 9 is also about the Fourier, discrete time. Fourier transform, and I would like to list the important properties of the discrete time Fourier transform. But before that, I would like to have this review of the synthesis and analysis equation that we have written. So the synthesis equation is about representing this discrete signal by the complex exponentials, so 1 over 2 pi, and the integration for the one period with this complex exponential. And then we had this Fourier transform analysis equation, where we do the summation for minus infinity to plus infinity of x of n times e to the minus j pi n. So this was called the synthesis equation. And the synthesis equation is about expressing xn as a Fourier transform. So you decompose the signal xn as the linear combination of complex exponentials with amplitude, which is proportional to Fourier transform. I'm going to write that down, okay? And also this is the analysis equation, where we obtain this x of omega by xn. So this synthesis equation is about, so it's worth writing it down because we are now reviewing. Decomposing the xn signal as linear combination of complex exponentials, complex exponentials with amplitude. And this amplitude is proportional to, no, it's not proportional, it's which is function of it's proportional to the Fourier series. I said proportional because you have to have this 1 over 2 pi and this delta omega to complete the amplitude. So it is correct to say proportional. My bad. And also please note that this x of omega is continuous even though xn is discontinuous. So it's worth writing it down. So this is a continuous function in the frequency domain, and also this is a complex exponential. Complex value. So because it's complex value, we need to represent it by the magnitude and phase. Or you can use the rectangular form, which is represented by real part and imaginary part respectively. That's your choice. However, a lot of books describe them by the magnitude and phase. The famous one was a Bode plot. So you might as well know this part. So the properties of the Fourier transform. So this was a quick review of discrete time Fourier transform, and we will go straight into the properties of the Fourier transform, of course in discrete time. The properties of the discrete time, the first one is the periodic. It's a periodic signal, which means I can represent large x omega by large x omega plus 2 pi m, where m is an integer. And this was not true for the continuous time, right? So, I mean, the set of complex exponential is periodic, therefore this x of omega is periodic. And since this is true in complex exponential, in the complex value, for complex value, both magnitude and phase are all periodic. So both magnitude and phase are all periodic. One more time, this is not true for the continuous time, remember? And it's symmetric. And this is the same thing as in continuous time. If xn is a real signal, which we are currently, which is in our scope right now, then we can say that x of minus omega equals the complex conjugate of x omega. And we can denote this as conjugate symmetric. And remember that we can say this as the real part of this Fourier transform has the property of even function like this, and also the magnitude has the property of this even function. remember that we have written this down during the continuous time Fourier transform property. Now I think you know what I'm going to write down right now. So for the imaginary part, you have to put the minus sign front to make the equality, because it has the property of the odd function, and also for the phase too. For the phase angle, you need to put minus sign here. So it's a huge difference. So you had odd property, you had odd function. Okay. So I would like to remind of you for the example that we did to express the properties of the periodic and symmetric. So remember this example that we just did. And if you obtained the Fourier transform, then you get this function. And if you plot this function with respect to the magnitude and the phase, then you will get these two plots respectively. And you can see that the magnitude and phase, they're all periodic, right? They are all periodic. So if you truncate by minus pi to pi and minus pi to pi, you can see that this part repeats for the rest of the frequency domain, right? And also you can see the symmetry property for these two. So for magnitude, you can see that this is an even function. It's symmetric with respect to y-axis, and you can see that this phase angle graph symmetric with respect to the origin, which means it's an odd function. So please, you need to distinguish between these two. And also the periodic thing did not happen with continuous time function, continuous time Fourier transform. Okay. For discrete time, as we did in the continuous time, you have time shifting property, which is if you shift the time by n0 in time domain, then if you do the Fourier transform, then it becomes the phase shift. Like this. So I told you why this is the phase shift during the continuous time properties, so I'm not going to repeat that again. Also, the property called frequency shifting is also the property for a discrete time, where if you do the phase shift in the time domain, then you get the shifted frequency by the amount of omega 0, like this. So you can see that this time shifting And this frequency shifting is in the sort of duality relationship, okay? Now you know what it means when I say duality. Okay. And I'm gonna go through this part quickly because we already done these parts during the continuous time. So linearity property also is valid for discrete times. And if you do the Fourier transform for the linear combination of two discrete signals, you get the same linear combination with the Fourier transform of each signal respectively, like this. And this was about the linearity, and it has the exact same property in continuous time. The Parseval's relation also is also valid for the discrete time. So it's about the energy in time domain is proportional to the energy in the periodic Fourier transform. So I'm not gonna do the proof also in this time. I'm not gonna do the proof, but write down the statement. So if you do the summation of the square root of xn, then that equals 1 over 2 pi integral of just one period of Fourier transform squared, square root of Fourier transform. So this means that the energy in time domain is proportional to energy in periodic Fourier transform. Okay, so this is about the Parseval's relation. And also, remember the great thing about the convolution. You have the same property for the convolution. So if you do the convolution in time domain, which is about passing through the LTI system, remember? Then this becomes a simple multiplication in the frequency domain, which is a beautiful thing. And if you have this LTI system, which can be represented by this impulse response, remember the impulse response was represented by this letter H, okay? And if you have the Fourier transform of this impulse response, which is represented by this capital H, and if you have an input of xn, then the result can be obtained by the convolution in the time domain. However, in frequency domain, it can be represented by this simple multiplication. And furthermore, if I have this same LTI system and I would like to select the input as the complex exponential, recall that the complex exponential is the eigenfunction of the LTI system. So eigenfunction of LTI system. And you get the same, what? You get the same complex exponential with the same frequency here, which is multiplied by h of omega 0. So you have same eigenfunction. We wrote down this stuff a couple of times, right? A couple of times, but I would like to repeat this because it's a very important part. And this large h of omega 0 was called what? It's called the eigenvalue, right? It's called eigenvalue. And the frequency, the Fourier transform, this is the Fourier transform of impulse response, right? H of n at what? At when? At frequency being omega 0. So please don't forget this one. I know the mathematical derivation is very important, but I would like to make an emphasis on the intuitive interpretation also. So xn can be represented by this linear combination of complex exponential, and that amplitude was proportional to x of omega, right? So this complex exponentials with the amplitude proportional to Fourier transform. I said this proportional because you have to divide by 2 pi and also multiply by d omega, right? So if you process this signal through the LTI system, then the only thing you have to do is multiply by this frequency response, h of omega, which is the Fourier transform of impulse response. And this impulse response is all about this LTI system. So that's the important intuitive interpretation. Okay, I think I will stop here for today and continue this chapter in the next video. Okay, I'm sorry about that importing the pictures. It took a lot of time during our lecture. I'm very sorry for that. And please, please remind the difference between the continuous time and discrete time Fourier series and Fourier transform. And also, there are a lot of same properties for the continuous time and the discrete time. However, there are some difference among them. So please keep that in mind, and we will continue our work in the next lecture. Okay, again, thank you very much for your attention. And if you have any question, please let me know by sending me an email. Okay, I don't go through the Q&A tab in AjuBB, so please directly email me if you have any question. Okay, thank you very much. I'll see you in the next video.